All right, let's talk about Saturn. Saturn is, as a semi-major axis A equal to 9.6 AUs, it's about exactly twice the distance of Jupiter. Remember, Jupiter was about 5, so it's almost exactly twice the distance, which gives it a revolution period of close to 30 years. It's 29 and a half years. So most of you students have not lived one Saturnian year yet. You have to reach 30 years old before you're one Saturn year old. The mass of Saturn is 94 times the mass of the Earth. Remember, Jupiter was 320, so mass-wise, Jupiter is about 3 times more massive than Saturn. However, size-wise, they aren't all that different. The diameter of Saturn is 120,660 kilometers. Remember, Jupiter was 140-some thousand. So it's bigger, but it's not a lot bigger. But it's got a lot more mass. Jupiter does than Saturn does. So what that means is Saturn has a very low density. It has by far the lowest density of any planet in the solar system. It has a density of only 0.7 grams per cubic centimeter, which means this is less than the density of water. And since it's less than the density of water, if you had a big enough ocean and threw Saturn in, it would float. Truth is, none of that would ever work. Once you had an ocean that big, then the gravitational field of the ocean would affect things, and it's mostly gas, and the gas would get dissolved by the water. So, but the theory is there. Just remember, it has a density less than water, which means it's very just gas. Okay. Its rotation period is about 11 hours. It also shows differential rotation, just like Jupiter does. In fact, all of the Jovian planets do. They're subtle, but you can see these lighter and darker cloud bands just like you see with Jupiter. And since you see these lighter and darker cloud bands, we're getting differential rotation fastest around the equator, just like we see with Jupiter. This picture I'm showing you right here, the greatest image of Saturn yet, this was from the Cassini mission, which went to Saturn and studied. In fact, it studied for almost 20 years before they finally said, okay, well, Cassini's running out of power, we're losing it. So they actually just ran it through the ring plane and then crashed it into Saturn to say, hey, let's see what we can find out before it dies. But what it did, and this is a huge image, I downloaded this image, but you don't get all the detail here, but it's like 65,000 pixels across. It took me like all night downloading. I probably shut down the whole campus to download this one image. But it was super high resolution. You lose that when you project it onto a screen here. All right, so let's look at more pictures of Saturn. So this is a different picture. This one you can clearly see the cloud bands better. Right here, these are moons of Saturn. Saturn has lots of moons. In fact, it has the most moons of any planet. It has more moons than Jupiter even does. And I'm not even sure what the latest count is. I think it's like 80 or 90 moons now. It's just so high, and they keep finding more. But yeah, we'll talk about the rings later. The rings are the coolest part of Saturn, but let's talk about the planet. Saturn is even more oblate than Jupiter is. It means it's more stretched out than Jupiter is. The distance this way is significantly less than this way. Because it's still rotating nearly as fast as Jupiter, lower density, it tends to flatten even more. So if you measure the distance across here and a distance across here, they're not the same. Okay? It's not a sphere. It's what we call an oblate spheroid. Somebody squished the ends of the ball. You see these cloud bands. Well, the cloud bands again occur from the same thing. You're seeing different molecules. In fact, you're seeing the same molecules. So if we look at the interior structure of Saturn, it's very similar to Jupiter. You have a small core in here, solid core. Then you have a metallic hydrogen layer And then you have this molecular hydrogen layer. And those same molecules that we saw in Jupiter are in Saturn because it's made of the same stuff. So we see water, methane, ammonia, ethane, all these ones that all of them have hydrogen in different levels. Now the biggest difference though is because it's twice as far from the sun, it gets 1/4 the amount of solar radiation. So you start to get really cold. The tops of the clouds out here are about 97 degrees Kelvin. Remember, you got to get up to 273 just to get to freezing of water. So this is very, very cold. You're talking minus several hundred degrees here. So it just doesn't get much solar radiation out there. And so the missions, all the missions they sent to Saturn, and any of them beyond that, you can't power them with solar power. In fact, even at Jupiter, you really can't power them with solar power. You don't get enough solar radiation to power solar panels to charge it up. You can do it at Mars, but beyond that, you pretty much start to lose it. All these were powered with radioactive materials. It was just a little piece of radioactive plutonium, which gives off heat, and then that heat uses a thermal conductor, which changes heat into electricity, and it runs the whole spacecraft. The good thing about that is it runs for long, long periods. You can make it run for hundreds or even thousands of years off of it. But it doesn't give off a lot of energy. All right. Here is Saturn from the edge. So what we have to do is we got to look at the orbit of Saturn, because we find that it changes. Now the first one to see Saturn's rings was actually Galileo, using his telescope. But he didn't have a really good telescope, so he really couldn't tell it was rings. In fact, he thought it was like ears. He thought the planet had ears. And then at one time he thought it had two moons right next to each other. In fact, he drew a picture in his notebook. He thought it looked like this, okay, with ears. And then he realized later that they were gone, that those moons just disappeared. Well, we now know from going backwards, because he kept what date he saw it, what really happened was he just saw the rings edge on, and so in his telescope they completely disappeared. He thought that was perfect because Saturn, if you go back to your mythology, Saturn was the one that gave birth to Jupiter and all the other ones, other gods. But instead of them, he knew they would overthrow him one day, so he would eat them. And he thought, oh, Saturn just ate its moons, or ate its offspring. All right, now they were gods, so it didn't hurt them. And they eventually did overthrow Saturn and take over, and Jupiter became the reigning champion. But what happens is this. Here is the sun. Here's Saturn's orbit around the sun. As Saturn goes around, it has the rings like this. It has a tilt. Okay? And because of that tilt, so its north pole is going this way and like this. When Saturn is on this side of its orbit, we see the top of the rings. But as Saturn orbits around, that tilt stays the same direction. So over here, the rings become exactly edge on. And when they're over here, we see the bottom of the rings, or the south side of the rings. And then it disappears again. So during this 30-year period, what we do is we see the rings on one side, then they disappear, and then we see the rings on the other side, and then they disappear, and then it comes back again. So about every 15 years or so, the rings disappear. That's when they usually find most of the new moons. It's like, oh, when you get rid of the rings, they find these little rocks and go, oh, hey, there's more moons out there. And this is the shadow of moons on Saturn. And when it gets exactly edge on, it is pretty much impossible to see the rings. That just shows you how thin the rings are. You can't see that ring in front of the planet there. This is the shadow of the ring, because the sun's a little bit above it. The shadow of the ring that you're seeing on the clouds back below it. But the actual ring is above that, and it just pretty much disappears because it's very, very thin. Very long, very thin. All right, so that occurs regularly. Let's look at some more closer up pictures of Saturn. there's a few things that you want to notice here. Here's the rings too. We're going to talk about that in detail. This one has a good picture of the ring. Notice there are gaps in the rings. We'll come back and we'll talk about those too. But then you see the different cloud band layers. Very subtle. Why are they so subtle as compared to Jupiter where they're really bright? It's just because the lower temperature means the colors all get kind of subdued. They're all much paler. Same molecules, they just don't show up as much when you get them down to only 100 degrees Kelvin. And we've seen some weird effects. We do see storms on Saturn that come and go. Not as big and prominent as Jupiter, but we do see storms on Saturn. Here is a storm right here. You see, showed up and then it went away. This is a Hubble Space Telescope picture, so that's pretty much about as good as you get from the Earth. And as for the same reason we have different colors, is because you're seeing different layers in the atmosphere. Very similar to Jupiter. The only real difference here is the scale of this has changed. All this is at different altitudes, more compressed together for Jupiter, and the temperature is more extreme here. So that's the biggest difference here. So when you're out on the surface here, this is in Kelvin, you're only at about 80, 90 degrees Kelvin. That's very cold. It does warm up as you go in. Remember, 300 Kelvin, 330 Kelvin or so, that's the human temperature. So, I mean 310 Kelvin or so, give it in that range is about human temperature. But this is cloud layers, okay? And ice layers, you should call them, they're clouds, but they're clouds of ice droplets. Because it's so cold, they're in an icy state. They're not in a liquid state at all. All right, here is Saturn II. They call this the dragon storm. Does that look like a dragon? It's kind of weird. When you're astronomers, you got to get creative because you see the same thing over and over again. So you use a lot of imagination when you see things.